Now, before the 18th century, this is a little bit of history so that people can appreciate where this thing, we have what we call the vitalism or the vital theory, which was believed that organic compounds can only be obtained from living organisms. Antimicrobial resistance, as currently projected, that it is now the third leading cause of death in the world. And, World Health Organizations, European journals have also predicted that if the problem of antimicrobial resistance is not addressed, by the year 2050, it is going to be the world leading cause of death.
Hi, everyone. Welcome to today's episode of Let's Talk. Again, I am excited to host our guest for this episode, Dr. Isaac Antwi. In our previous video, he shared with us his insights on raising more young African scientists. He also shared about some of his personal experiences, the challenges that he has had to deal with, and his achievements. And yeah, so definitely check out that video. I know you would learn a lot and it would also inspire you to keep moving in your career. If you have already done so, then stay tuned for today's conversation with Isaac. On this note, welcome again, Isaac.
Thanks, Emelia.
Great to have you. So we are going to talk more about your research today. What is your area of specialization in chemistry, and what are the different branches within, like subfields within chemistry? Because I tend to think when we think about chemistry, we may probably think it's just one whole field, but there are a lot of specializations within that. So could you educate us more about that?
Thank you once again. My area of specialization to answer and to elaborate more on is synthetic organic chemistry, basically put organic synthesis or organic chemistry, depending on what you want to see with, which I think maybe if time permits, I can talk more about it. But to answer your question about the various divisions or aspects of chemistry, there are a lot of different aspects of chemistry. The commonest one, but not limited to this, I'll be saying, is inorganic chemistry. It's also an aspect of chemistry, which basically talk about inorganic. Organic, mostly think of natural things from, so anything that is not from nature, we can say it is an inorganic. We have the environmental chemistry division, which mostly studies things about environment. People are interested in pollution and other stuff. We have the physical chemistry, which mostly deals about the theoretical aspect, of chemistry. And we also have the computational chemistry as well. So they use computational methods to study chemical reactions or how processes of chemical reactions are, occurring. Chemical biology, it's also another aspect that blends the chemistry and then biology together to study how compounds interact with molecular on the molecular level or with biological substances. So these and many more are the areas of chemistry, and even within these areas there are specialities. So somebody might be in an environmental chemistry but will have his or her specialties in environmental chemistry. That will be different from another person in the same environmental chemistries with different specialties. But on a broader sense, these are the major aspects of chemistry that one can think of. So we have the organic chemistry, the inorganic chemistry, the physical chemistry, the analytical chemistry, the environmental chemistry, and chemical biology, which I believe they are either aspect of it, but not limited to these. These are the major. And I happens to find myself in the organic chemistry aspect of chemistry.
Wow. So what are some of the questions that your research seek to answer?
Yeah, that's good. And before I come into my specialties, just to let viewers know or appreciate organic chemistry, what it is.
Yeah.
So it's basically studying the structures of organic compounds. Now, before the 18th century, this is a little bit of history so that people can appreciate where this thing. We have what we call the vitalism or the vital theory, which was believed that organic compounds can only be obtained from living organisms. So that was what was perceived. So we call it vitalism or the vital force theory.
Okay.
But around some time, there was a lot of questionings going up, and scientists were really asking, is it true? Is it more like a vital? We can only get organic compounds only from living things. So in 1828, that's where the first time an organic compound was obtained from an inorganic source, which was carried out by anybody who take basic organic chemistry will know Frederick Wohler. In 1828, he was able to synthesize urea, which in chemistry, the opaque name, you call it a carbamide. And he did that from an inorganic source. So he used the salt of potassium cyanate and ammonium sulfate. These two things I am talking about are all inorganic compounds. And so I'm able to take or make this or urea, which is organic compound, from inorganic source, broke the whole idea or concept of vitalism or the vital force theory, that we can only obtain organic compounds from living things. So that sets up the space for people to really think further of ways of getting. So the history behind organic chemistry cannot be told without talking about the achievement of Frederick Wohler in 1828. And subsequently, William Henry Perkin and other people made so many contributions in 1856, making quinolines, and we have come this far, and we know that organic compounds is not only obtained from organic source, but can also be obtained from inorganic source. Now, my specialty with organic synthesis was to study how antibiotics, which we all know what it is, interact with cell membrane. And so antimicrobial resistance, as currently projected, that it is now the third leading cause of death in the world. And World Health Organizations, European journals have also predicted that if the problem of antimicrobial resistance is not addressed, by the year 2050, it is going to be the world leading cause of death, with an approximate 10 million deaths annually from globally. So it is a major concern. And the commonest cause of antimicrobial resistance has to do with the misuse and abuse of antibiotics. I know there are other, forms or, factors that brings about resistance or whatever, but major cause has been attributed to the fact that people misuse or overuse antibiotics. And so in my PhD work at the University of Alberta, my work sought to come out with either antibiotics or antimicrobial compounds that will be more potent in the fight against antimicrobial resistance, and potent in the sense that even if these compounds will develop resistance, it should be in the longer term. We know that it is hard to prevent resistance from happening, but we can come up with compounds that have slow resistance. So, I mean, if it's the current drug takes like, let's say, a month or two, why can't we develop compounds that even if resistance will be developed, it will be in the year 2, 3 or so. So one aspect which it has gained momentum in the area of antimicrobial is antimicrobial peptides. So peptides basically are amino acids that come together. So scientifically, they have been assumed that if it's about 60 amino acid, we call it peptide, and anything above 60 or 70, depending on whatever you're reading, we call it a protein. So you have amino acid which come together. And lipopeptides, it's one of the class of peptides that have shown activity or improvement in the fight against antimicrobial resistance. So when I joined the VEDRES lab at University of Alberta, there was a preliminary studies that was being conducted on one lipopeptide that we call it tridecaptan, which from the studies have shown that it was active against both gram-positive and gram-negative bacteria. If you have a compound that is active against gram-negative, then it is very promising, because those are the bacteria that are difficult to, fight. Gram-positive bacteria are not so challenging to fight. And so my task and my PhD career was that this compound we know interact with lipid membrane, but how do they interact on the molecular level? So I investigated how these antimicrobial compounds, which specifically was tridecaptan, interact with the lipid membrane. And here I'm talking about lipid 2, which is the cell wall precursor of the lipid membrane. So I made the antimicrobial compound tridecaptan, and I also made, so let me say synthesize, as because I'm organic, so synthesis is the same as you make, and made the lipid 2 and analogs of lipid 2. And we were using an instrument called nuclear magnetic resonance, NMR. So what the NMR does is that we can use the NMR, the nuclear overhost effect, or how these elements within the compound sees each other to really map which atom or which amino acid of the peptide is closer in proximity to the lipid membrane. Then we can do some studies. So in simple put, my work sought to come up with more potent antimicrobial compounds that will have lasting resistance to gram-negative and gram-positive bacteria. And it was accomplished using the tools of organic synthesis as the medium. I also was interested in small molecule compounds. So my first publication was a small molecule compound, which also showed activity against some strains of bacteria. So in all, we were seeking to address the problem of antimicrobial resistance by coming up with antimicrobial peptides that are active against gram-negative bacteria as well as gram-positive bacteria, in the aim of solving the problem of antibiotic resistance.
Wow. Thank you so much for taking your time to start with us, like explaining what organic chemistry is, and then breaking it down to share your research with us. Thank you. And I also want to ask, with the increase in the COVID pandemic and other like deadly diseases, I strongly believe that there is the need for more chemists or like people that work on producing drugs. Were these things, something that motivated you to the kind of research you do?
Yeah, I mean, that's great. And the pandemic for sure has shown the need to invest into research and development. And I would say that it has even strengthened my desire and passion into the area of contributing to research and development that aims in identifying potent drugs to fight against common disease. And I remember in the pandemic, somewhere around March, my former university, that's where I did my PhD, went on a shutdown. But our research group happens to be working on a COVID-related program research, and I happen to be part of it. So seeing everybody in the house being scared to work out, and every day driving from house, go to the lab, carrying out research, I was so excited that, my contribution is also needed in the midst of all these challenges. And I always talk to people back home and, ask the questions of some of the diseases that kills young ones. Growing up, for example, I have seen young people who have lost their life due to the lack of medicines available. Some of the deaths that we've seen over the years, if there were enough or drugs available, especially in Africa, some of the deaths would have been avoided. And so anytime I look up, around the world and look at where I come from in Africa and the disease that are coming up, I always get motivated that I want to be part of the problem solving community. And one way is that my research is focused on targeting or addressing a problem which needs resource, it needs people. So I would say that yes, the COVID pandemic had shown, and scientists, chemists, for example, or people who are into pure research mostly are behind the scene. You go to the drug, you're giving paracetamol, all is it. But it starts from somewhere. It starts from the lab-based experiment, then it moves to the industrial commercial base, and all these are research and development, and that is where some of us belong. And that is where all the thinking, and not disregarding the work of other people who prescribe or administer, but I want to emphasize that the scientists or the research and development scientists play significant role in the fight against various diseases or even all diseases. Everything starts from that small round bottom flask, and then it transfers and moves into some palate that some are sweet, some are bitter, that you take, it goes in you, and then the next day you are jumping. The chemists, the chemical biologists, the molecular biologists, and all the research scientists who are not in the forefront, as we might see, play significant role. And I believe that our goal is that common disease shouldn't be the cause of death of people. And I know that with how science is projecting, you'll get to that point.
Well, thank you so much for doing what you do. And to all the other chemists and professionals that are working on producing drugs to help fight against deadly diseases, we do appreciate you, even though we don't always get the platform to show that form of appreciation. So back to your research, would you mind telling us some of the fascinating results that you have had throughout the course of the researches that you have dealt with?
Yeah, it's interesting, for example, in the area of antimicrobial resistance, which is a difficult problem. And I remember, one of my projects seeks to synthesize this small molecule compound, which we came up with the name cycloalonapine. It was first, isolated from milk of cows in China, and they reported that the compound showed or had activity or could inhibit the growth of both gram-positive and gram-negative bacteria. And so once that paper came up, we were interested, as synthetic organic chemists to really know which isomer of the compound. So basically what the authors did was they reported the generic compound without any stereochemistry. When I say stereochemistry, I mean that, in chemistry, if you have a carbon center that has 4 different groups surrounding it, then that carbon center is classified as stereogenic. So you can have 2 stereogenic centers, either the R or S, and these are just nomenclatures. But the authors didn't report. And in that compound, we had 2 stereogenic centers, and we could have 3 possible compounds because 2 of the compounds will be meso compounds. Like when we say meso, it means that they are the same. So let's say if you look into your mirror, your right hand side becomes your left hand side. So you can just juxtapose them on it in the mirror as it is. So in the mirror, that right hand side, it's the same as your actual left hand side. So we say that those 2 are meso compounds. So we sought to make these pure compounds and know that and identify which of these 3 compounds was really active against these strains of bacteria. So, I embarked on the synthesis, which initially I anticipated it was going to be easy because we had a simple compound with a molecular weight of, I think, 158 grams per mole. And, we could think of a simple chemistry. However, the initial attempt wasn't successful. And it took in 6 months of trying to figure out myself, and then my postdoc who I was working under, it wasn't possible for us. So we thought of abandoning that project and started, a new project. But along the line, as I gained experience in the lab and I gained experience in research, I revisited the project again with a different route, and by literature research, I came out with a method that was able to help me to make this compound. We made this compound, which my boss was so excited because this was almost about 2 years down the line that we thought we've abandoned the project. And coming back to be able to make these compounds was, amazing. We tested these compounds against strains of bacteria. Myself and my collaborator, Dr. Sorina Siren, who was a chemical biologist in our lab, who is currently a postdoctoral research fellow at Scripps Institute. She did the biological test of this, and the results weren't so great as we anticipated. The antimicrobial or the minimal inhibitory concentrations were not so great. But our ability to come up with that synthetic method to use common hypervalent iodine reagent to perform a cyclization of 7-membered compounds, which are very difficult to make, was something that was, interesting and serve as a precedent for people or any other person who wants to form hydrazide in that manner could always refer to our synthetic approach. And even though the chemical biology aspect of it, which we thought this compound, if it had great activity, could push forward to make it a possible antimicrobial compound, didn't go so well. But that doesn't stop there because we only tried just few amino acids. We only tried 3 amino acids, alanine, glycine, and lysine. And there are many amino acids which could be used in that same synthetic manner to obtain similar compound and possibly can come out with a more active compound. So more structural activity relationship studies can be enhanced on that compound to really come up with a more potent. So publishing that result and coming up with that synthetic method to make that 7-membered ring, to me was, a great achievement. And anybody who will see that compound will think of everything that we all thought of. Oh, you have this, you can form a diester, you can hydrolyze one, activate the acid and do cyclize. All those things that every synthetic organic chemist could think of that we thought of weren't successful up until we saw that hypervalent iodine reagent was used to make cyclized hydrazide. And to me, anytime I look back, it's always, it's a success to me. I would say that.
Wow, I'm glad to hear about that. And also talking even more about the antimicrobial resistance. You already told us or educated us on how deadly it is. So what is your advice for antibiotic abuse? We see this to be the case in a lot of countries. You go to the drugstore and you just get an antibiotic, and people keep abusing it. So what is your advice for that? And what do people need to know about the risks of abusing these kinds of drugs?
Well, my advice, is that we should not overuse and misuse antibiotics.
Yes.
We should be aware that even the strongest antibiotics that we resort to have developed resistance, right? So it becomes even more worse when you take, these antibiotics in an inappropriate manner or you misuse them. I would say that, let your, health practitioner or your doctor prescribe. Don't just walk into a pharmacy and, which I know it's common, especially in Africa, that people just walk into drugstores, tell, oh, this drug worked for this person, and so give me this or whatever, without any prescription. If we are able to do these things, I think we can reduce the rate of antimicrobial resistance. And that is in the aspect of humanity, or we being responsible. It can also be that scientists and researchers should also, take this as a threat, a global threat. Yes, we might not see it as we know now, but it is gradually getting there, and it's even currently being the third leading cause of death. To tell us that possibly more research should also go into this area and to look into, because there are so many sources or ways, or we can come out with antibiotics even in the seas, oceans, trees, soils. Natural products which have antimicrobial activities are all over, but we need more research to go into it. And with that, we could come out with more potent, and then coupled with people not abusing and misusing it, I think the problem of antimicrobial resistance can be addressed. So it's more of both individual role, government role, and also the scientific community have a role to play in the fight against antimicrobial resistance.
Wow, thank you so much, Dr. Isaac Antwi. It has been a wonderful session with you on both talking about your passion to inspire other young ones and also discussing your research on synthetic organic chemistry and the work that you have done on antimicrobial resistance. It has been a wonderful time with you. To our viewers, we are glad that you were able to stay till the end. Until our next video, let us enjoy science together. I remain your host, Emelia. Thank you.
Thanks, Emelia, for having me on this platform. It's an honor and privilege.
Great.